So, welcome to lecture number 26 students, and so we have been discussing about the properties of nanomaterials for the last 10 lectures, and so couple of more will be going on for the properties of nanomaterials. As I have been interacting with you during online sessions, I found that some of these topics are not easy for you to understand, because you may not have read or probably have been exposed to these topics. I would like to tell you one thing very clearly: nanomaterials is indeed a subject of multidisciplinary nature. That means it encompasses fields of physics, chemistry, engineering, biology. So, therefore, it is not possible for you to understand everything when you study this subject at the first time, but you must make an effort to learn as much as possible. That will be my suggestion to you for this. Today we are going to discuss mostly about the optical properties of material. And in the last lecture we completed our discussions on the magnetic properties of materials, and we shall start a new topic on optical properties of nanomaterials. Before that, we need to have some recap. What we did, we just talked about the effect of size on the two important properties, that is coercivity and remnants, and then we also deliberated on superparamagnetism as well as superparamagnetism, how the size can make a strong effect on the evolution of these new properties. Super word means high or extra, right? The superparamagnetism means very extreme level of paramagnetism, or superparamagnetism means extreme level of paramagnetism. Please do collect your questions and keep it for the interaction sessions. In fact, I must tell you, I am not satisfied with the interaction sessions. I expect you to ask me more questions so that we can discuss and learn more on these subjects. Well, magnetic materials divided into diamagnetic, paramagnetic, ferro or perimagnetic based on the magnetic moments. Okay. So, when you apply magnetic field vis-a-vis when you do not apply magnetic field, in diamagnetic materials effect is not at all significant. Zero magnetic field, there will be no effect. When you apply magnetic field, the diamagnetic materials normally oppose the magnetic field. That is why we call these materials, we do not discuss much of these materials. That is what something you should remember that. But that is not the only issue about the paramagnetism, diamagnetism. There are all the materials in the world show some kind of a diamagnetic behavior because of the spin, electron spin around the nucleus. Now, second class of material is paramagnetism, the paramagnetic. In absence of magnetic field, they show random spin alignments, but when you apply magnetic field, there is some kind of alignment happens, but alignment is weak. So, therefore, magnetic moments are very weak. So, normally they are not useful. The useful magnetic materials are ferro or perimagnetic. In case of both these materials, the spins align for both zero and non-zero magnetic field, and for the non-zero magnetic field, spins can be aligned in a particular directions very nicely. This can lead to very high magnetic moments, and these are used. Difference between ferro and ferri in terms of strength of these up and down spins of these materials, that we have discussed already. So, by the way, for the ferromagnetic materials, if you apply field, the magnetic induction happens, and the magnetic interaction follows a certain specific train. So, basically this has happened because of the alignment of the domains or the spins along the applied field directions, and the domain with aligned magnetic fields magnetic moment grow at expense of poorly aligned ones. So, that is why initially it rises and then it reaches a saturation when all the magnetic moments align to the direction of the applied field, and this is very common, and this leads to what is known as a BH loop, we popularly call. This is H, magnetic field is induction, So, you see this is what is shown here, and then it goes back like this, okay, then it comes back like that. So, that is the magnetic loop. Depending on the size of this loop, we can actually have soft or hard magnetic materials. Soft magnetic materials will have very thin loop with a small value of coercivity. Okay. This is what is known as a coercivity, and this is what is known as a remnant magnetism, right, that we know. So, this is all the important things. Saturation reaches once you value apply certain field, then you have a coercivity. Coercivity is the negative field required to demagnetize the material. Remnants is when the field is 0, some amount of magnetic moments remained, that is all is called remnant. This is the general appearance of magnetism curve. Magnetism curve exhibiting histories is loop shown there, and the important parameters already I have told about it. Okay. So, now why does it happen? As we discussed, this is because of the domain alignments to the field, and domains cannot be very large, then it is energetically very expensive. So, therefore, there will be domain walls, or what is known as a block walls, and in block walls actually demarcate the spin reversal, okay, or spin change, as you can see here in this case also, in this case also. So, in a multi-grain materials or a poly-grain materials, you can have spins align in a different way in one grain itself, like you can see here, the grain size is pretty big. And that means what, in the grain you can have several domains present, and each domain corresponds to certain domain wall, and they are differentiated by domain wall. So, therefore, there is energy associated with it, and that is something which is very important. So, that means when you apply, when you talk about effect of size, what actually happens? Big size, there is no effect, okay. There is only both coercivity and the remnants, there is no effect. But as a size, because they are very big particles, and they have large number of domains present in each of these grains. So, therefore, both the coercivity and remnants does not change much with the grain size, but there is a range below which both of them shoots up. Why? That is because then your particle size become very small, and each of these single particles will become a single domain particle, right. That is what it is, a single domain particle happens, and then there is no domain wall exists between in the particle, because this is all single size is so small that the one domain is one particle. So, because of that, remnants and the coercivity increases very rapidly and reaches a very high value, correct. But as you reach a smaller size than that, the thermal effect comes into picture. Okay. So, remember this alignment of the spins basically created by the magnetocrystalline anisotropy, right. That is nothing but equal to K into V. V is the volume, K is the magnetocrystalline anisotropy parameter. But at the same time, you have a thermal effect coming into picture. Because of temperature, the thermal randomness try to play a role, and this can make the spins misaligned, okay, or spins to be randomly aligned. It can randomize the spins basically, the effect of temperature is, and this can lead to reduction of the alignment of the spins in a direction of the field, and that can lead to reduction of the coercivity remnants drastically. In fact, it can reach 0 value also below a certain size, critical size. So, that is what is very important, and that is what we have been talking about it a lot, and you must remember that this size thing is very critical here. I am plotting it again here. This is what is supposed the coercivity, and this is size. Okay. So, as you see here, what will happen is like this, you have no change, then drastic rise, and then there is a decrease automatically. So, that means there is a two domains or critical size. One is called D critical, below which single particles becomes single spin particle, okay, and there is a size below which superparamagnetism happens. That is what. So, these are the multi-domain particle, and these are the single domain particle. Okay. So, this single domain particles, once they align, spins align in particular directions, thermal effects can make them misaligned, and this can lead to reduction of the coercivity or remnants. This is what is shown here in a superparamagnetic material. You can see the spins are in each particle aligned differently, and therefore they don't add up to the magnetic moments. Okay, within a supermagnetic particle, the elements of magnetic dipoles are oriented parallel, but while magnetic interaction of the particle is negligible, orientation of magnetic moments of the particles are random, and this randomness leads to substantial reduction of the coercivity. On the other hand, you have superparamagnetic material, which can also possible in this domain, okay, in this domain here, okay, in this domain. So there, the superparamagnetic materials particles are equal size, and their distance allow them dipole-dipole interaction. That means each of these dipoles can interact with each other and make them align in one direction without any randomness, and these can lead to huge increase of remnants of the coercivity. That has been observed, and superparamagnetism also has been observed. Well, that's about the recap of magnetic materials. Now we go into, okay, by the way, yes, let me give you some example also, because this is something which is very important. These slides are taken from Professor Anand Subramanian of our department. He has put this on his website. Okay. As you see here, for nickel iron, when you have a size 0D, 1D and 2D and bulk, you can see from bulk to 0D magnetic moment is increasing very, very significantly. This is given as Bohr magneton per atom. Iron effect is even more substantial. Okay. So if you can have a maximum possible moment of 6 Bohr magneton per atom, 3 orbital and 3 spin, but it means what? The 0D material is very basically it gives you the limit of orbital magnetic moment. Okay. So that means what? Effect is very significant for this type of materials which are predominantly ferromagnetic. Well, this is again shown in a very nicely manner. Okay, you can see the bulk behavior, then it increases, superparamagnetism behavior comes in picture, then the thermal disorder takes it over, and then what is happens? The coercivity goes to 0. So these dP is corresponding to superparamagnetism, and ds is called to single domain particle, that lead to superparamagnetism basically. And for the superparamagnetic material, you have a BDH loop like this, because there is no remnants or there is no coercivity, so therefore there is no possibility of any BH loop in these cases. Well, that's about the magnetic materials. You have spent about 12 to 15 minutes on that. Let's talk about optical properties. Let me first tell you how I am going to discuss about this particular topic or particular aspects. First, I am talking about some aspect of optical properties of materials. Then I look into the size effect, okay? Because I understand some of you may not have exposed to optical properties extensively. Well, optical properties is something to do with light. Light is what? Light is a form of energy detected by an eye, and at ordinary scales can be treated as a wave basically. It's nothing but a wave, we know. Light waves are basically part of electromagnetic spectrum, which you will see soon, and then it has many, basically it can be described using an equation like this. This is the epsilon y is nothing but the amplitude of the wave, that's equal to epsilon 0 into cos twice pi lambda x minus bt plus psi. Phi is basically a phase factor. So it's basically equation between space and time. Okay, x is the space variable and time is the t. So that's what is the light can be described as a wave formalism, but light also can be considered a particle, as you know. In quantum mechanics, light is considered as a particle, and so therefore, but in the case of optical properties, mostly it is considered to be a wave. What is the electromagnetic spectrum? By the way, it starts from radio waves to gamma rays. Radio waves can be very big, like meters, even it can reach actually 1 to 100 meters, and then you can have microwaves, which is in the range of centimeters. You have infrared, which is in the micrometer to centimeter, millimeters, and then you have ultraviolet, X-rays, and gamma rays. But in between this infrared and ultraviolet, we have light waves. Okay, the wavelength varies from 700 to 400 nanometers. 700 corresponds to red, which is the highest wavelength possible, and 400 corresponds to basically violet. So electromagnetic spectrum has these small range. So one is that we have visible lights, or lights can be, the colors can be seen by our naked eyes. Well then, but in a nutshell, it can also include, when you're talking about optical properties of nanomaterials, it can also include ultraviolet also. but it will not include X-rays, infrared, microwaves, gamma rays, okay, when we are discussing about optical properties of nanomaterials. Please keep in mind that aspect. Well, you know, how does the material and the radiation interact? You know, when any electromagnetic wave falls on some body or some material with intensity I, and this intensity depends on the amplitude square of, you know, wave has amplitude, and amplitude square is what is gives you the intensity, and you know, so therefore the intensity tells you the measure of energy the wave carries. So when the radiation is intensity I0 strikes a material, a part of radiation basically reflected, part is absorbed and part is transmitted. So these things means IR is basically corresponding to reflection, IA is absorbed and IT is transmitted. This is what happens. So if I divide IR by I0 plus IA by I0 plus IT by I0, this must be 1. That means what? Whatever the total radiation falling on any substance or any material, it is going to be either absorbed, reflected or transmitted. But these three added intensities will be equal to intensity corresponding to incident beam. Okay, that's very clear. Okay, that's something must happen, otherwise energy will not be conserved. So how it interacts? If it reflects, you know, light falls at an angle and then reflects with the same angle. If it's refract, light falls on this interface, then it's is the direction of changes. Okay, you can change that. Okay, right. It can also have both reflection and refractions, and on a basically rough surface, reflection will happen at different angles. Okay. Okay. So therefore, depending on whatever things happening, it can be described in this format, in this way, how the interaction happens. So the next important thing is the absorption. That's about reflections and or refractions. Radiation can penetrate any material. If it can be penetrated, then only it can be absorbed, right? So greater the thickness through which the radiation passes through, greater is the absorption. This is something also very interesting. The larger is the thickness through which the light is passing through, more will be absorption. So therefore, intensity of light, which is starting with initial value I0, can decrease basically by this equation, I0 exponential minus beta x. This is very, very standard equations which has been followed in optics for a long, long time. And here beta is nothing but the absorption coefficient. So that means basically if I plot I by I0 versus x, this will be exponential curve with negative sign, because beta has a value, positive value. The absorption coefficient depends on basically wavelength of the light passing through the material with the color corresponding to wavelength that is absorbed. That's why thick slabs of ice looks blue. Okay, thicker the slabs, it absorbs more. Therefore, it absorbs more means you have blue of light will be coming out of it. Okay, so that's something which is very common. So you understand that this is the absorption equation which is normally used in most of the kind of experiments. So what about transmissions? Okay, so we have discussed about reflections, we have discussed about absorption, we are discussing about now transmission. By the time a beam of light has passed completely through a slab of material, it must have lost some intensity because of reflections, the surface which is entered, and also because of absorption in between. So its intensity will be obviously like this. Okay, you can clearly see this equation comes okay the second part because intensity lost to reflections by the both surfaces. Okay, that's why. So that's why it has to multiply twice. That's why the square come. Okay, R is corresponding to reflections, and I0 exponential beta is basically absorptions. Okay, you understand that, right? So this is very simple equation, but normally you have not seen it. That's something which you should remember it. And I have explained also why the square comes into picture. So now let us talk about this absorption and transmission effect in a material. What happens in a material? Metals normally absorbs photons because metals have a lot of free electrons. Basically, electrons are not localized and they are not bound to a particular atom, so they are like a free electron gas. So the metals can absorb easily photons, capturing the energy by promoting the electrons from a field part of the conduction band to the higher empty level. That is what happens. If you put a photon, this electron will absorb this photon and go to the higher part of the conduction band. Okay. And when the electron then falls back, a photon is re-emitted. That is what you see here. Correct. That is what the interaction happens when it absorbs and it re-emits. Okay. And emission energy will be same as like the decrease of the energy because of the this jump from the higher to the lower. Now, dielectrics, okay, like basically insulators, they have full band. That means their valence band is full, conduction band is empty, right? That is what happens. So, what happens when you put when you basically shine them with the light? So, therefore, what will happen? Material cannot capture any photon. Okay, so therefore, it cannot capture photons with energy less than delta gap. Okay, the gap whatever is between the valence and the conduction band, it cannot absorb. So, meaning that for those frequencies, material is transparent. Okay, if you are shining the lights with frequency corresponding to energies less than E gap, then it will not absorb. It will allow it to transmit through. But it is better, because why to absorb the energy which are not going to be useful, right? So, that means the material will be transparent to those frequencies, but photons with energy greater than delta E gap will be absorbed, and then it can, the electron will go to higher energy level in the conduction band, and once the electron jumps back to the valence band, energy is released. This is something which is very frequently observed in materials. So, you can see that optical properties of bulk materials can be explained very easily using these band theories of electrons, the conduction and the valence bands. Well, what about reflections and dispersions? Reflection also important. Refraction basically, not reflection. Refraction, I am sorry, this is wrong. This should be refraction. Refraction is apparent binding of a ray of light when it enters a transparent medium. So, this is a water or glass. Okay. The magnitude deviation is obviously given by the refractive index, and that is nothing but n1 is equal to sin theta 1 by sin theta 2. The angle is this. You could have seen this picture. Okay, this is sin theta 1 and sin theta 2. Okay, that is this what it tells you about it. The equation is known as a Snell's law. All of you have studied in your class 2 physics or maybe in class 10 standard. This equation is a special case of general relations that applies to light passing through the medium of refractive index n1 to n2. There is nothing but sin theta 1 by sin theta 2 is equal to n2 by n1. In amorphous materials such as a glass or a crystal with a cubic symmetry, index of refraction is same in all directions. There is no difference of refractive index because of crystallographic directions. They are called optically isotropic solids, but some other crystal basically this is not so. So, they are called optically anisotropic materials. So, that is about the refraction and dispersions. Now, you also have luminescence and phosphorescence. Emissions of radiation by solid relatively low temperature is called luminescence. Photoluminescence is what? The light emission brought about by absorption of high energy photons, typically ultraviolet rays. The most widely utilized form of photoluminescence is fluorescence, in which light emission is immediate and taking via allowed transitions. Phosphorescence is what? This is similar to this photoluminescence, but is differentiated by slow conversion of the excitation energy into light. In case of photoluminescence is very immediate. Okay, it is not be slow, it will be very immediate, but in case of phosphorescence it is slow. Like all those of you have seen the any microscope, scanning electron microscopes or maybe transient electron microscope, electron falls on a white screen and then you see the pictures. This is nothing but a phosphorescence. You have a phosphor screen with which the electron interacts and then it gives you light. So, light emission is delayed here in case of phosphorescence, and that is basically because of the light emitting transitions. Some are formatting, some are allowed, some are not formatting, and that makes the delay. But photoluminescence is empty number of light emission modes available, so that is why it is immediate. Okay. These are the things, two things you must remember. Okay, they are not same. Some of you always will tell photoluminescence and phosphorescence are same. They are not basically same. Well, there are different types of luminescence: photoluminescence, triboluminescence, chemiluminescence, cathodoluminescence, sonoluminescence. It depends on the source of energy basically. So, if you have a radioactive source, the decay is the main thing, it is called radioluminescence. If it is applied electric field, it is called electroluminescence. All kinds of luminescence are possible depending on the energies. Okay, so that is something which gives you some amount of introduction to the subject. Now, optical properties of material, size effect. Well, by the way, size effect comes into pictures in 3 ways, okay, for the nanomaterials. What are these things? There are 3 things happens in nanomaterials, and basically optical absorption are always associated with 3 important aspects. Optical absorption in nanomaterial, let me write it. In NM, it depends on 3 factors. Okay. First one is the density of states in valence and conduction band. We already have discussed that density of states or DOS in valence and conduction band. Right. Second one is what? Second one is basically what is known as a quantization of energy levels or quantization of energy levels, right. In a nutshell, this tells you the quantum confinements, energy levels, or I write down quantum confinement. Right. And third aspect is what? Third aspect is a new thing. It is exciton effect, which is new, which I have not discussed so far. And this is mostly happens in case of semiconductor. So, DOS, you know that density of states in valence and quantum bands, that is what dictates the electronic transitions, and electronic transitions are basically responsible for optical spectrum, optical absorption. Okay. And in nanomaterials, you can have quantum confinement effects because of the size or because of the dimension of the nanomaterials. That has a strong role to play. And third thing is exciton. So, first let us talk about what is exciton. Okay. What is it? You know, let us talk about a semiconductor with a certain band gap. It is easy to understand in case of semiconductor, so I am taking this example. Otherwise, I could have taken examples of insulator. Okay. So, as you know, semiconductor has a band gap, and this is shown here, this band gap, right. So, therefore, if I have incident photon energy which is higher than the band gap, what will happen? Electron will be excited from the valence band, and then it can jump into the conduction band, which is mostly empty in case of semiconductors, okay, at room temperature or low temperature. They are empty mostly. So, photon energy is higher than this band gap. Electron in the valence band absorb the photon energy and then excite it to the conduction band, correct. So, and under these conditions, photon is absorbed very easily, correct, while a hole is left in the valence band. Once the electron leaves the valence band, it leaves a hole there. So, if inversely an electron in the conduction bands returns, suppose electron in the conduction band returns to the valence band, what will happen? Okay. So, it will recombine the hole which is present there, and then photon is released with energy equal to the same as the band gap of the semiconductor. So, these two things can happen easily the moment you have a photon energy which is more than the band gap. So, photon energy can excite the electrons in the valence band, and then it can go to the conduction band. Okay. So, one is goes to the conduction band, leaves behind a hole in the valence band, right. Similarly, the electron in the conduction band can jump back to the valence band, recombine in the hole, leaving behind the photon energy. This is a very standard thing, can happen in a bulk material like a semiconductor. Am I clear? Now, question is, how by low temperature, what has been observed for the bulk semiconductors? It shows often this optical absorption. Just now we discussed absorption of these optical photon at a just below the band gap. You don't need to excite these electrons in the valence band by energy of the photon higher than or equal to the band gap. It can actually get excited even very lower than or very close to the energy band gap, just below the band gap energy. So, this something which is against the intuition just now I told you. Why does it happen? Well, this process is basically leads to a new concept. That is why it happens. What this process is associated with the formation of an electron and hole bound to each other. Okay. Am I clear? This process basically, because it is happening at an energy level lower than the just below the band gap, this can lead to formation of a species which combines electrons and the electron and the hole, and this bounding state of electron and hole is known as a exciton. Okay. This is what is known as exciton. Okay. So, you understand that. So, that means electron and hole can bound each other, they do not recombine and produce a photon energy. They just bound each other and remain there. As for the many particle, exciton has mobility. Obviously, it can, even this whole thing can move as a recombined, as a combined thing, not a recombined thing, combined thing. And binding between this electron hole is because of the electrostatic things, electric charge between the electron and the negative charge and the hole positive charge. So, therefore, the Coulombic energy is nothing but minus E square divided by 4 pi epsilon 0 r square, right. So, here E is electronic charge, epsilon naught is basically dielectric constant for the free space, and r is the separation distance between the electron and the hole. So, it basically tells you an electron and a hole can remain together without recombining, and that is what is known as a exciton. The reason they remain together is because there is a bonding, electrostatic bonding between them, positive charge of the hole and negative charge of the electrons. They can basically attract each other, and then they can have a Coulombic interactions. Okay. Now, electrostatic interaction, basically this electrostatic interaction between the holes and the electron can reduce the energy required for the excitation formation. Okay. And that is what causes this effect, that even if you have a photon energy which is below the band gap energy, still this phenomenon can happen. Electron can move into the conduction band. Okay. Electron can get excited. Okay. So, that is what can happen. Electron can get excited even if you put an energy which is less than the band gap energy of the material. So, that is what it is, and so therefore, the electrostatic interaction will reduce the energy required for the excitation formation with respect to the unbound electrons and the hole energy, bringing the electron energy level closer to the conduction band. Okay. What is that? Okay. Well, this is something which I need to show you. So, therefore, electron, once it jumps here, it can recombine and gives a photon. That is what we said. But electrons may not jump here, it can remain here, okay, do not recombine and create an electron hole pair. That is what is known as basically. Now, just now what I was said, because of this electrostatic interaction between the hole and the electron, what can happen? This can lead to reduction of the energy required for the excitation formation with respect to the unbound electrons or the hole energy, that is the band gap energy basically. So, bringing the energy level closer to the conduction bands. Okay. These energy levels will be electron hole energy levels will be closer to the conduction band, because because it has a already attractive force. So, this can lead to reduction of the energy levels or the band gap energy, and So, that means what? The energy band for this excitation will be closer to conduction band. It is same thing like if you have a impurity in the silicon. The moment you add an impurity, energy band, sorry, the energy levels of the impurity can go closer to the conduction band, and that can lead to easy transfer of the electrons from the to the conduction band, right. That is normally observed in case of this. But nonetheless, as a result, the basically Bohr radius increases. Okay, you know the Bohr radius basically. So, Bohr radius increases, and the new Bohr radius is normally Bohr radius is given by this excitation Bohr radius epsilon RB m naught 1 plus m v by m naught. You know, this v means relativistic, and epsilon naught mv, right. So, U is the dielectric constant, epsilon naught is the basically the dielectric constant at this p space, RB is the Bohr radius here of the absorption of the excitation in the absence of excitations, this RB, okay. And mg is the mass of electron, m is the effective mass of electron, and mh, oh sorry, this is mh, so this mh will be mh, oh, this is m0 is the mass of the free electron, me, this is me is the effective mass of the electron, and mh is the mass of the hole. That is what it is. So, this equation is a little bit complex, but this is a modified Bohr radius. And as you can see here, this table for the different material like copper chloride, cadmium sulfide, cadmium selenide, gallium arsenide, even silicon also, the excitation radius are in nanoscale, right. So, therefore, for a nanomaterial, excitation radius may be confined, because the dimension nanoscale. For nanomaterial, this radius can be confined also. The interaction between hole and electron can be modified. This is something which is very, very new to you, right. You may not have heard about such kind of concepts, but it is nicely given in chapter 7 of Asby's book. You can read it up and understand. Okay. So, in general, so this is what is called excitant, and this can affect it, the optical property is very significant, right. So, let us talk about these aspects in next 10 minutes or so in a little manner, correct. So, as we have discussed, the three effects or three things which can affect the optical properties of nanomaterial. First is the DOS, density of states in the valence and the conduction bands, okay. And second is these quantum confinements of the electronic level, energy levels because of nanostructuring, and third is this exciton. An exciton actually basically has a diameter basically is nanoscale or dimension like 1.3 to about 20 nanometers. So, therefore, these can actually lead to what? This can also be confined, just like electrons can get confined, electron energy states. The exciton energy states also get confined depending on the nano material and the dimension. Okay, so how does it can be observed in the real scale? Okay. So, you know, as the nanomaterial changes from 3-dimensional to 0-dimensional, quantum confinement is very severe. You all of us seen that, okay, in our last discussions on even on magnetic properties or electrical properties or even thermal properties. These effects we have already seen it, right. So, therefore, as the dimension decreases from 3D to 2D to 1D to 0D, this quantum confinement becomes very severe, and it can lead to very density of states become quantized, and the band gap of the material can shift upward. Okay, it has been seen. So, as a result, you can have blue shifts, okay, in the absorption spectrum as the size of the material decreases, and red shift when the size of the material increases. This is what has been observed also, and this is understandable, because as the energy bands are getting quantized, the band gap will be increasing. It will go to higher upper side. As the band gap increases, you have a blue shift, okay, and as the band gap decreases because of size increase, red shift happens. So, effect is more visible in this picture which is shown here. You see, this is nothing but a room temperature optical absorption spectra of lead selenide nanocrystals with different diameters. starting from 3 nanometers here, A corresponding to 3 nanometer, okay, and the H corresponding to 9 nanometers. So, B is again 3.5, this is 4.5, this is 5, this is 5.5, 7, very close spaced size ranges of lead selenide crystals. Okay. So, what do you observe here? As you see here, the visible this basically shows the highest absorption region. Okay. Shortest wavelength corresponding is 1000. So, therefore, this is the highest absorption regions. Okay. And look at this band, what is happening, it's slowly shifting to the lower size. And when at lower size, you can't see even this band at all. This band has moved below 100 nanometers wavelength or so. That is something which is always up. That is what is called blue shift, correct. As the size decreases, this absorption edge corresponding to the absorption highest energy absorption region is shifting to the blue region, that is shifting to a lower wavelength regions. Okay. You remember the optical spectrum, red to blue, right? Red 700, blue is 400. So, blue is lower side. That is what is called as the blue shifting. Okay. So, these kind of absorption edges are shifting towards the lower wavelengths. That is what is called blue shifting. Am I clear? As the particle size decreases, and this is understandable. Why? Because of the quantum confinement of the electrons. As the size decreases, electrons are getting more and more confined. So, electrons cannot take up the energy levels which are allowed at higher values than at lower values. You see, at 9 nanometers, the confinement is much less severe than at 3 nanometers or 2 nanometers, right? That we know, because as the size decreases, confinement become very serious, because your it's basically nothing but related to in the potential well, this is the x is equal to 0, x is equal to L, right? So, this is the length, right? You know the energy En is proportional to L square, right? Energy El is corresponding to 2m 0 L square n square h square pi square n square, right? That is what you see. So, this as you decrease the L, the energy E, okay, is more severely confined, right? This is a factor of L, right, as you can see here. Although it depends on n, but the confinement basically, as you plot E versus n, if you plot that, okay, n is equal to 1, n equal to 2, n equal to 3, the nature of the energy curve will depends on also L, right. So, that is what I am telling. As the size decreases, this effect will be more significantly felt than for this absorption edge. Finally, for the higher absorption peaks like this one, okay, this is the higher absorption peaks here. Higher absorption peaks are associated with the formation of exciton. Okay, this is something which to understand. This is low absorption peaks can be easily understood using this density of states and the quantization of the energy levels because of the size effect. But higher absorption peak cannot be explained by that. It can only explained by the exciton, and which can shift to lower wavelengths. As you can see here, it is shifting from 2000 to about 1000, close to 1200 nanometer. Okay, that is what is this absorption band is shifting. Okay, this peak is slowly shifting. You can clearly see that. Okay, this peak is slowly shifting that side. So, this shift is can be understood using the exciton. Okay, just now I discussed what is exciton. It's basically combinations of electron and holes together, and they are bound together because of the electrostatic energy between themselves, which is nothing but a Coulombic force. Now, question is this: how this effect is observed? Well, that's why I need to discuss this. We always consider two regimes. One is called strong confinement regime, other is called weak confinement regimes. So, weak confinement and strong confinement regime determine basically degree of coupling between the hole and the electron. How they are strongly bonded. That depends on the distance, obviously r square. Depends on the media. What is that called? You have seen probably, no? That depends on this distance r square, and depends on this epsilon 0. E is obviously constant. It does not change for the electron and hole. So, anyway, so that means the strong and the weak confinement will depends on how they are strongly they are bonded with each other. Well, let us now discuss each of these cases and then we can wind up this lecture. Correct. So, so therefore, in case of weak confinement, a dimension of nanomaterials are greater than the exciton radius. Okay. They will be at least greater than a factor at 1 or 2, okay, at least double or triple. So, exciton radius is 1.3 to about 5 or 6 nanometers. So, particle size should be double of that, at least 12 or maybe it can be 3, 4. If it is 1.5, it should be 3, and if it is a 6, it will be 12 nanometers. Okay. So, if it is so, then this can happen. Under these conditions, Coulombic interaction between the electron and the hole leads to increase of the excitation energy, binding energy, okay. And obviously, this causes a shift of the exciton peaks towards the blue, okay. Because electron hole are binding very strongly, that energy, which is the binding energy between the electron hole, can shift the energy level to the higher sides, and that can lead to blue shift, okay. Higher energy means lower wavelengths, okay. You know that its energy is nothing but E is nothing but what? H C by lambda, right? That's nothing but H nu. So, the higher energy means lower wavelengths, okay. The band it goes to higher energy levels compared to the valence band. So, therefore, the blue shift happens. Am I clear? And this is what we see here. But on the other hand, higher degree of confinements is observed in case of, but these confinements will be very easily filled in case of nanofilms or nanowires than the nanoparticles, correct. But on the other hand, if the dimension of nanoparticles are bigger than, smaller than the excitation radius, then this whole thing will be not correlated properly. That means the excitation will not exist at all. That is what is called the strong correlation or strong confinement effects. So, weak confinement effects is more widely seen. Weakly they are confined to each other, but when the size is smaller than the exciton radius, this effect will not be seen. So, that means this absorption spectra is very important tool to investigate the optical behavior of the nanoparticles. Okay. So, with this I stop here, and then we will come back with some more on the optical absorption spectra in the next lecture, so that you will understand. But before I wind up this lecture, I would like to say these are the things which are really new to you. You have never probably come across such a kind of concepts, but fact is that these are used in your research area. So, it is better you learn these aspects and at least try to understand how they can form, how we can explain them, and what is the effect of size on these properties. Thank you.